Right, good evening, everybody. My name is Tanya Reinhardt, and on behalf of the University of KwaZulu-Natal, I would like to welcome you to our last online talk in celebration of National Science Week. Over the last days, we opened the doors to the UKZN Ivory Tower, and we hope that we showed you what scientists really do. Before I introduce our guest speaker for this evening, just some house rules. Please make sure that you have muted your microphone. So the microphone is at the bottom left, and if it doesn't have a red line across, please click on it and mute yourself. Also, because of the bandwidth issues that we might experience, if you can just also switch off your videos, it's right next to your microphone button where you mute yourself. We will have a question and answer session. So please, if you can just post your questions and wait for the question and answer session to ask your questions. Just a little bit of background on why we're actually here. It is all about the celebration of science, the celebration during National Science Week. And National Science Week is an annual celebration of science, engineering, and technology. And we are attracting thousands of learners and members of the public to workshops, science shows, and lectures, which are held at universities, schools, science centers, and public facilities countrywide. And because of COVID, we unfortunately have to do it online. We used to have like in-face communication there. The Department of Science and Innovation leads the initiative, and the South African Agency for Science and Technology Advancement, NRF-SASTA, is responsible for the implementation of National Science Week. Each year there's a different theme, and activities usually revolve around this theme. This year's theme is making it possible through science. And the last days really showed how fitting this year's theme has been. So, for example, Professor Brooks talked about UKZN's road to success in aerospace propulsion research, and Ms. Mercer's talk about the hardship of developing and implementing radio telescopes on a tiny island called Marion Island. And believe it or not, it belongs to South Africa. And now it is an absolute pleasure to introduce our guest speaker for tonight, Professor Andrew Greene. And Andrew, I know Andrew when he was still a student. And he will conclude the trip into space by coming back to Earth and showing us how he lifts the water to do something that I'm very passionate about, and I know that he's very passionate about, geology, so looking at rocks. So a little bit about Professor Greene, about Andy. So he attended the University of Natal, where he received a BSc in geology. Then he ventured a little bit on the side. He did a BSc Honours in Environmental Science, but we had the pleasure of catching him back, and he concluded his MSc in Marine Geology. He was then awarded with a PhD in Marine Geology from UKZN in 2009, and he is currently the head of the Marine Geology Research Unit at UKZN and a full professor in geological sciences. He was a Fulbright Scholar in 2018 and a recipient of the 2019 American Geophysical Union Africa Award in Ocean Science. And I think that speaks for itself about his class. He has published 85 peer-reviewed papers in the field of marine geology and graduated more than 20 MSc and PhD students. And rumors has it that he does like pina coladas, but does not like getting caught in the rain. The title of tonight's talk, Lifting Back the Waters, Adventures in Southern African Marine Geology. And I'll leave Andrew the stage.
Thank you, Tanya. Let me just try and get myself organized here. So let's do some screen sharing. Okay, I'm going to minimize that. All right, can everybody see me and can everybody hear me?
Yes, Andrew, we can see you. Not you, but yeah, we can see you and
sure, carry on, Andrew. We can see you.
Okay, excellent. So thank you, Tanya, for the introduction. And I must say thank you very much for inviting me here to give this. I think this is a wonderful opportunity to exactly do what the title says, to lift back the waters. As geologists, particularly marine geologists, that's what we aim to do. We aim to lift back those waters that obscure what lies beneath and try and understand what occurs in the seafloor and beneath that. And obviously this is an exciting thing to do, lots of adventures to be had. But this is a real pleasure to be able to have an opportunity to give this across to an audience. It's so varied and diverse. Okay, without further ado, I think I need to step into a little bit of background here. So whenever I mention to people that I'm a marine geologist, the very first thing that springs to people's minds is this. And unfortunately, no, usually people say, oh, great, with the dolphins and the whales. And though dolphins and whales are interesting, it's not exactly the crux of what marine geology is. So if this is what you're tuning in for, unfortunately, I think you're going to have a fairly disappointing 45 minutes thereabouts. Really, as marine geologists, we're interested in the seabed. We want to understand what that seabed's made of. Here we have a beautiful looking seabed. Basically, this is a nice rocky outcrop, and growing on this is a whole lot of coral. We're not so much interested in the coral, though the coral is, of course, interesting, and oftentimes the things that grow on the seafloor are related to the geology, so we do work hand in hand with biologists. But on the whole, we're more interested in what lies beneath. And we can have bedrock on the seafloor. We can have, oh yeah, we've got talking Andrew Greene blocking the way. Let me move that. We can have things like gravel. So this is a sediment core that's been taken offshore of Durban. So a core is much the same as like a cork in a bottle of wine. We drill down with a series of pipes and we pull out a portion of the seafloor that gives us a vertical profile into it. And here we have one of these, and it's made up of all sorts of pebbles and little bits of angular rubble. You can imagine that's quite interesting for all the little nunus that might live or explore in there. We can have seafloor that's made of things like sand. People are obviously quite familiar with, or even things like mud. Each one of these has its own properties and its own importance in terms of how the seafloor behaves. We're also interested in the seafloor from its shape. So here's a flat line. Unfortunately, it's also a little obscured. The seabed is not always flat. In fact, the seabed undulates quite a bit. And that's important to understand because those undulations are oftentimes controlled by things such as sediment delivery or erosion from ocean currents or by waves. Understanding the shape of the seabed is a particularly important facet of marine geology. Not only the shape, but we're also interested in the structure of what lies beneath that. So we've got a series of little layers that I've drawn in here. Each one of those layers is interesting to geologists because they mark a step back in geological time. We're allowing ourselves to walk back in time and to look at each individual layer as a change in Earth history. As a geologist, that's exactly what you want to see because we are interested in examining and understanding a dynamic Earth. So this is the crux of things. Unfortunately, no dolphins and whales. So why map or even try to understand the seafloor? Well, this sprung about because we are a sea-going species. So eventually we evolved to the point where we began to navigate around our coasts and then to cross the oceans. And in doing so, we discovered that there are a number of hazards that face us in terms of this navigation. And things like rocky outcrops or shallow areas, or where we have large waves breaking because the seafloor suddenly shoals. And we end up producing things like this, where we have shipwrecks. And these early maps that are created around us are stemming from this. The very first attempts to try and visualize what the seafloor looks like from a depth perspective. So, that's exactly what we're going to talk about for most of this lecture, is really like understanding the depths of things, and that we refer to as bathymetry. Obviously, to making these maps and exploring, guys were looking for dragons and the end of the Earth. And if you believe in dragons and the fact that the Earth's flat again, perhaps this is not really the talk for you. Just bear with me, okay? So how do we actually go about mapping or understand something we can't see? So human eyes are not adapted to open and look through water and see a seabed that's perhaps a kilometer or even several meters beneath us. So we need to rely on remote sensing techniques to do this. And one of the earliest ones, and this is a picture actually describing this in detail, this is out of a historical archive, is from using something called lead line techniques, where we had like a very heavy weight, like a lead line attached to a rope. This would be dangled off a boat until the lead line touched the seabed, and we could then measure how long that rope was and would give us a rough idea of how deep that little piece of seafloor was beneath us. You can imagine that this isn't ideal because firstly, you're going to need biceps like Popeye, really strong, very physical work. And, if you have ocean currents operating, that thing can be swept away in a diagonal line. So you're getting an over-reading or an under-reading of something. So it's not ideal, but it can give you a reasonable approximation. And those maps that we saw earlier were made from just this. And this continued all the way through until even the early parts of the 20th century. Each one of these points that you collect in terms of a depth reading is something that we refer to as a sounding. So we're getting soundings or depth readings from the seafloor. And, in many instances, it was actually a lucky thing that we had World War II, not because of the carnage, but because the massive technological advances that came out of this. This was at a point in time where suddenly scientists realized that they could be bats. We use now the principles of echolocation. Like a bat uses sound, it emits a little chirp of sound, that sound travels and then it bounces off an object and the bat receives it again. What we do is the same sort of thing. We emit a sound pulse from an emitting medium, we usually call a transducer, that travels to the seabed, it bounces back and is recorded. We know how fast sound travels in both air for a bat or seawater for us, and therefore we can work out using the miracles of science and equations, a very accurate measurement of the seawater depth. This is incredibly important to us as geologists, and I'll show you now in a second. This is the fundamental underlying principle of sonar, and I'm sure you've all seen this before. We've all watched, and I'm probably giving away my age here, The Hunt for Red October, all those submarine movies. We see the guys gathered around their sonar and it's going, etc. That's exactly what this is, except we use it in slightly different ways. So this technological revolution that came out of World War II spurred on mapping of our global ocean basins. And it came from things like trying to find U-boats and trying to find mines that are submerged within the ocean. And using this technique, we actually created a massive change in our scientific thinking of the way in which the Earth and the planet itself behaves. So this map here is probably the first real map of our ocean basins. It was created by something called a bathymeter, which is this electrical device used using echo sounding to understand the depths of the seafloor. We call it an echo sounder now. And the map itself was made by this lady in the bottom right corner here, Marie Tharp. Very important lady. It was her birthday just a few days ago. She compiled this map by hand and she had it painted over several years. And this map forms the crux for us understanding or forming the first piece of the puzzle to the theory of plate tectonics, that our plates can move around, they are in motion, and that the Earth's surface is actually an active area of deformation. We have mountain chains in the mid-oceans, and we have very steep portions of the ocean here where crust is being pushed under other pieces of crust. And this map allowed us to begin to think in a lateral way and start to visualize a new understanding of the way in which we see the Earth evolving. Incredibly important. So if I take you through some of the techniques by which we can actually look at the seafloor and estimate its depths. We've talked about the lead lines. Each one of those spots is a sounding, and we've been improving ever since. So then we moved on to the bathymeter or the echo sounder. We call these single beam echo sounders because we have a single means of producing a sound source, and that source is being reflected back, and we are then recording that. So the ship sails along in lines, and we actually leave behind lines or trails of soundings, and then we can interpolate between these using statistics for a best guess of what the depths might be between these. This is very good when you have very closely spaced lines, but not so good when the lines are very broadly spaced. And it was a big revolution in the 1980s that turned into a new way of understanding the seafloor arose. And that was where we took multiple echo sounders, put them all together to produce something called a multi-beam echo sounder. So instead of just one single pulse going down to the seabed, there are multiple pulses that form a big swath that then paints the seafloor with thousands and thousands and thousands of these soundings. Each time we pass by, we can paint a swath that overlaps the other swath until we have a full coverage of the seabed that gives us a complete high-resolution rendering of the seafloor in 3 dimensions. So if I can show you guys the progression and things, this would have been something like an abacus. This would have been something like my metric calculator that I inherited from my brother in 1996. Thank you, Mum and Dad, for that. And this would be something like the latest iPhone. Massive changes in technology. And this technology is still changing to this day. So I'm going to take you guys back to an important map that was made by an important guy. So this is a map made of one of our marine protected areas. This is Seduana Bay, the home of South Africa's living coelacanth, where it was first discovered in South Africa. And this has stemmed most of the ocean-going research that we've done since then. This map was made in the late 80s and early 1990s and is one of the first high-resolution bathymetric maps to ever be made. It was made by famous and very, very well-renowned marine geologist in our country, Peter Ramsey. And in this map, you can see he's visualized a series of submarine canyons where all of these are contour lines, so lines of equal depth. You can see they're all bunched together. That's very steep seafloor, with submarine canyons here. And less than 10 years later, we went back and we replicated that survey after the discovery of the coelacanth, and we produced this map. We can see now a huge difference. So this is now an artificial rendering in 3 dimensions of what the seabed looks like. And you can see what appears to be very large ripples. We actually call these dunes that are occurring on the seabed. We can see far more submarine canyons in the area, these big, funny cauliflower-looking things that are extending up into the shallow waters than was picked up here. Far better resolution of what this looks like. These big cauliflower heads of these canyons here. And it was exactly in here where the coelacanth was discovered. Interestingly, if we go ahead and we look at that in high detail, that's 2003, looking right in the head here of this canyon called Wright Canyon. Incidentally, we have an audience member from whom this is named. And we look at this now in 2013, 10 years later, and we can see again, technological changes have been so advanced that we can see even better the intricate details of the seafloor than what I thought was pretty good in 2003. So we going through ever-changing technologies, and with that, we are getting a better and better understanding of the seafloor every day, which is fantastic. We're also interested, not, as I said, just about the shape, but what lies beneath. And I think most of you are familiar with the term seismic surveying, and everyone steps back, gasping in horror because the whales and the dolphins are getting impacted. And perhaps, yes, true to some extent, but this is not for all seismic surveying. What seismic surveying relies upon is, again, making a sound pulse, but that sound pulse doesn't just bounce directly off the seabed. It penetrates through the seabed and bounces back off varying layers that have different densities, whether it be changes from sand to mud, or mud to bedrock, or whatever it might be. What it does is it reveals a series of geological layers that look just like this. So this is a real oil and gas type of seismic line that has been produced. All of those little bright wiggles you see on there are essentially changes in geology over time. And we get very excited when we see that because it allows us to reconstruct the geological history of the area. Obviously, this is not something that we use all the time. We cannot afford to collect data like this. It's extremely expensive. Rather, what we do at UKZN is we use a much smaller system, much friendlier to the dolphins and the whales as well. And this allows us to see contrast between things such as sand and bedrock. And in particular, in this one here, if we look at it, we can see this dark layer here following where my mouse cursor goes, comes along here, over here, dips down again, back here. Those are old river channels that have been cut into bedrock and have since then been filled by sediment and now covered in water. This tells us, just from an immediate inspection, that at some point in time we had rivers crossing this area in the last few thousand years. Immediately it gives us an idea of what's going on. How do we collect this? Well, we use a small system. We tow it behind a vessel, got a little float over here and a little listening device, and we essentially collect our data along those lines. Very dolphin and whale friendly. Not only do we rely on these remote sensing techniques, but there's no good guessing what the seafloor might be. We need to also, what we call ground truth it. We need to observe it. We need to keep our eyes on the prize. And obviously this comes about through things like scuba diving, and we can see an evolution here. I wouldn't want to get in the ocean in that. I think we're getting a little bit better here. And obviously today we're looking at something far more modern, but this limits us to about 50 meters of water depth. Anything deeper, oxygen becomes poisonous to us, and we end up also getting extreme buildup of nitrogen. You get nitrogen narcosis, you do funny things underwater, and likely also you can get the bends. So under deeper circumstances, we turn to this. So this is the earliest type of submersible, a diving bell. And obviously we've gotten technological changes that have made for very cool things to come about. So these are what we call submersibles, little self-contained submarines. They're mega expensive. That's a scientific term. So they're not for us South Africans, but if you are Bill Gates, you'll have one of these on your private yacht. I've driven past the guy who owns Google. He's got a couple of those in the back of his mega yacht. And if you work in like big agencies and like say sort of the European Union, or the United States, anything like that, this is something that you have in your repertoire, but maybe not for us. We use little remote operated vehicles that can go down coupled to a line with a video, and we can kind of see what's cooking on the seabed. So that's how we do things. But I think before we step into what it is that we're actually researching and what's coming out of it, I think a lot of you need perhaps some shaking of your concepts in terms of how you understand the Earth. So many of us think in lifespan. So maybe 100 years, everything is fairly static in that. We might have a drought, but then it gets wet again, so on and so forth. But as geologists, we know we live in a changing Earth, and it changes from minutes all the way through to millennia, all the way through to billions of years. And this is the big concept to understand. One of the biggest changes that we need to familiarize ourselves with as marine geologists is the fact that the medium in which the marine is operating, ocean, changes. And this changes because mean sea level changes. So mean sea level is that sea level today. If you were to go and dip your toes in at North Beach, that's where we are. And we can see over time, however, that this is day zero, this is us today. 18,000 years ago, sea level was very low, about 130 meters below present. It's gone up and down, regular and cyclic. This is the kind of thing that drives massive changes in the geology that's left or preserved beneath the ocean. And this is one of the key things that we try and understand when we are going through our research as marine geologists. We're very interested in particular at this time period here, looking at this point, the low point here, which we call the last glacial maximum. So when the ice was held up, the ocean waters were held up nicely in the ice sheets at its maximum extent, ocean levels are very low, and then rising up to the present day. So here's a very good indicator of those changes. This is a sea level curve. Again, this is day zero here on the right. This is going back in time to the left. This was compiled again by Peter Ramsey and another very famous South African marine geologist. He's actually from Northern Ireland, Andrew Cooper. They put this together. We can see that sea level in South Africa, as well as across the world, has fluctuated up and down. And we're quite keen on understanding how this has occurred. In particular, superimposed on that last rise of sea level up to present day is some serious catastrophic events that have occurred. And these relate to very large jumps in sea level. So when the ice sheets catastrophically collapse, it's not just a constant steady state process of melting, but instead these things just completely collapse at times. We have a massive influx of meltwater into the oceans, and this causes the oceans to rise in their elevations. And here we have a sea level curve that has been derived from the Western Pacific. And we can see that this sea level curve looks like a set of stairs. We've got periods here where it's flat. That indicates that it's very slowly rising. And we have very steep periods here, which indicate these rapid jumps in sea level. We refer to these as meltwater pulses, or MWPs. We have a series of these. And interestingly, this is derived from the Western Pacific. So we have a lot to offer from the subtropics, particularly South Africa, because we have no ice. We've never been influenced by ice for the last several billion years. And as such, when we see sea levels fluctuating up and down, it's basically because of changes in the ice caps, as opposed to our Earth's elevation being altered by ice grinding on top and then moving backwards and forwards. So it's a really good place to be as a marine geologist, trust me. So my first adventures in marine geology started with my immigration from the motherland across to South Africa. So here's me at my gran and grandpa's place at 4 Gus Brown Road in Warner Beach. We came across on holiday, and that was my introduction to the ocean. And ever since that point in time, I've loved the ocean. It's been a passion in my life, from just wanting to be in it to wanting to understand it. That was how I got into this, was just because I just thought it was the most fantastic thing in the world. But the real beginning of these adventures started for me when I finished my honours degree. I was looking for something to do. I'd been living in Australia for some time. I'd come back, and this crew of people over here in 2001 and 2002 were for me the beginnings of my career and the start of my education. You'd be surprised to know that marine geology, even much to this day, is not something that's taught at universities. The only university that actually grapples with it properly is the University of KwaZulu-Natal. This is where you come to study, to be a marine geologist. And it was these people here, these 4 guys, all of whom are alumni from the University of Natal, and in particular from a marine geoscience unit that was related. It's Alan Smith to the left, Peter Ramsey, the famous guy, Doug Slowgrove, who's our sonar engineer, and Warwick Miller to the right. And it's these people I owe a massive debt of gratitude to, because it was this nascency and the beginning of my adventure that started off with these little contract jobs that I was allowed to do with them. And this is where I learned everything. So what did we need when we did this marine geological work? Well, this is the exact rack that was produced with all the equipment back in, I think it was 2001, late 2001. We did a survey for Richards Bay Minerals. You can see the very old looking computers in there, strange looking devices. All of that has been replaced nowadays by essentially a laptop, which is really incredible. That just goes to show you the evolution from dinosaurs to human beings in terms of technology and marine geology. Of course, over here, I think we do have a can of Dogem sitting. This is in northern Mozambique. Shame on you, Doug Slowgrove, for doing that. But you can see a massive change in the way in which we look at things. Of course, some things do stay the same. If you look there carefully, it says no cell phones. And hopefully that rule carries its way all the way through to our lectures. Thank you, undergraduate students. So what are our key areas of interest at UKZN? Well, it's really understanding sea level. Sea level from the aspects of looking at coastal deposits and coastal evolution over thousands of years. How do we do this? Well, often when we look at sea levels in very short time spans, so through the Holocene, which is maybe the last 11,300 years or so, we look at rocks that have been deposited above sea level. These are coastal deposits that have been lithified to form lithified beaches, imaginatively termed a beach rock, and aeolianites, which are lithified coastal sand dunes. We know where these lie relative to sea level when they are being deposited, and they give us very good indicators of how sea level has fluctuated over time if we get very precise dates on these. Likewise, too, if we look below where mean sea level is today, this is a very poorly understood part of our geology across the world. It's very, very difficult and expensive to get down there and to look at the seabed, to sample the seabed and to map it. So I can't just get in my car, go out and do some mapping. I've got to charter a ship, the very cheapest of which is probably 25,000 Rand a day. I've got to pay for petrol. I've got to have equipment that's in the millions and millions of Rands category. So this makes things very difficult to really get a handle on what's going on as sea levels being lower than present here. Quite interestingly, when we look at some of these beach rocks, little bits and pieces are sometimes interbedded or intercalated with them. They're mixed in with them. You can see here, this is the beach rock. If any of you live in Umhlanga rocks, you should be familiar with this. If you go down to the estuary, every now and again, this is exposed. We've got this strange looking speckly rock over here. What that is, it's an oyster reef. It has been ripped up. So lots and lots and lots of oysters have been growing offshore at some point. These things have been ripped up and mashed up by what appears to be a very high energy event and deposited in this old beach that's sitting here just at about mean sea level. What we think this is, and this is speculative for now, is that it might be evidence for a tsunami. This deposit we can map all the way into southern Mozambique almost continuously at various outcrops along the beaches. And it dates roughly to about 4,500 years, which is where we are finding literature pointing us to a catastrophic meteor impact in the Indian Ocean at that time. Obviously, that's the kind of thing that would generate something like this. Really not large looking tsunami, bringing and ripping up all sorts of things off the seabed and redepositing them slightly inland. So quite an intriguing little bit of geological evidence, therefore, just how the coast can change over just a few thousand years. If we look again at a set of beach rocks, here's one of my PhD students. She's sitting on a lovely beach rock. In the background here, underlying all of this, we've got an old beach filled with pebbles and cobbles, and it's indicative of storm events. So if you go down to the beach nowadays, you walk along and you've had a series of big waves, oftentimes exposed as a series of cobbles and pebbles that are left behind. That's exactly what's been preserved there. Then overlying this, we've got what we would refer to as a fair weather beach. So during nice fair weather conditions, we've had this beach then grow back and reestablish itself. Strangely, you can see here, there's no beach here. This was an old beach, but now this is a rocky coastline. That's just in a few thousand years difference. If we look at the surface of this, and this is what I think is kind of cool. Again, how interesting marine and coastal geology can be. So this is a three-dimensional picture we've made, taking a whole set of photographs and creating a three-dimensional model. Exactly just here where my student is sitting of a series of human footprints walking along this lovely fair weather beach. I always find it kind of interesting that probably wasn't so nice to be there when all the storms were occurring and we were getting all these pebbles and cobbles deposited. But once the weather cleared up, somebody back in prehistory decided they were going to go for a walk along the coast. What this means to us in terms of archaeology is uncertain. We need to date this still. I mean, if these date over here during the Holocene period, probably not all that amazing, but if they date back here at about the 120 to 100,000 year period, this is very important because that marks very early occupation by man in Southern Africa. And we know that we have occupations at a place called Seduana Cave, which is just inland of KwaZulu-Natal, and of course then further south at Pinnacle Point and Mossel Bay. But we haven't seen anything like this, evidence for this, as far north as the northern KwaZulu-Natal coastline where this locality is. So quite exciting. So all of this is based on the idea that the present is the key to the past. Without the present and without applying logic to what we see in the present, we cannot ever unravel what the past means. So we need to unravel what the present is in terms of what various beaches and those kind of things look like. And here's a modern beach. We can see a whole series of black layering in there. Those are heavy minerals. And I'd like to repeat here now, not oil, heavy minerals. So that's the kind of thing that Richards Bay Minerals mines. And we can see that's the modern, and we go back in time to the ancient. This is exactly the kind of thing that you expect. This is a beach rock filled up with these heavy minerals, pretty much looking exactly the same, just now lithified. If we see this, we know that it occurred in a very similar type of setting to this beach that we see today. If you guys are wondering, this was on Schlunga Rocks probably about a year ago. The next thing I'd like to talk to you guys about in terms of our research, and we'll tie all of this up, I promise, together, is our interest in coastal lake and water body evolution. So these have been a big interest to us at the University of then Natal and now KwaZulu-Natal for many years, because they give us a good window into the evolution of these systems from when they were once rivers to when they are estuaries, then to coastal lakes, and how these things interact with changing sea level. So here we have Lake St. Lucia, a beautiful image here of its terrain. We've got a seismic line that's been collected in there. And in here, we get a series of river channels that have been cut, and we can follow these out onto the ocean itself, onto the continental shelf. We can see these things have then been interacting with these submarine canyons, and again, interestingly, home to the South African Coelacanth. So important to understand. And so these things all interact together. And that kind of synergy and that interaction, again, just raises massive scientific questions for us. And we're really thrilled to be researching these. And in particular, these provide excellent archives for changing climate. They're dangerous to work in, as you can imagine. There's hippos, there's crocs, and there's the occasional shark. But more so, there's these things. And I think some of my colleagues here, Professor Humphreys, I know you're in the audience, these are the most miserable creatures in the world. There's nothing worse than working in northern KwaZulu-Natal during the summer. And we've been there every summer, unfortunately, for I don't know how many years. So how do we do this? How do we visualize what's going on in these like coastal water bodies, these marine, like these semi-marine type features, the lakes themselves on the lake bed? So let's go through some of the trials and tribulations of how we answer these questions. Well, we do geophysical surveys, so we use seismics to understand what lies beneath. And so here is our research vessel. That's what RV stands for. Pray we don't capsize. We have a rubber duck here that's probably suitable for maybe 300 kilograms of weight, and we've got about 1.5 tons of weight in there with all the equipment. I don't know how we didn't drown. We also use a big bar with a coring system, a barge with a coring system mounted on that. So that allows us to take samples, those vertical samples that we can pull out of the lake bed. We can analyze those. This is towed. I really was quite proud of this caption. This is towed here by Professor Humphreys' his speedboat from the University of the Witwatersrand. So this is towed around and we anchor it. That's where you usually get the worst sunburn and the best horsefly bites. And this is where we get dirty. So this is the actual sampling itself. It's really gross. Lots of mud involved because you really want mud. Mud is the best kind of thing to give you good climate change signals. And of course, this is all very labor intensive. So as I'm reaching the early 40s, I notice I'm starting to get arthritic. So to all my students out there, in particular to my collaborators, my time behind the piston core is coming to an end. So this is where we need to exploit you guys as cheap labor. So students, please apply. We're always happy to take you out on these field trips. Usually quite fun, but also quite tiring. So what of it? What about our results? So our results are always muddy, but they're always interesting. So what we reveal here is we reveal a situation, and I'm going to focus on Lake St. Lucia, even though we've been extending our studies all the way up into even southern Mozambique. We find very little sediment occurring in Lake St. Lucia. It's mostly underlain by just bedrock, and the bedrock limits essentially how much volume of water you can store in these systems. So the system itself is always going to be very wide and very shallow, which predisposes it to these sorts of episodes. So to drying up. And we can see here, here's a satellite image from 2016. You can see that the lake itself has been segmented into a series of isolated little basins. And these yellow spots here are where we've taken some of our core samples. Sorry, that previous image there is basically a map to bedrock that we made using the seismic lines that we collected. You can see that the seismic lines show very little sediment accumulated. These red bits are where we have maybe 60 meters of sediment, and those are all related to old river channels. Everything else is just rock. So where we've taken these cores, we also took in the deepest parts of these little segmented basins. And interestingly, when we looked at these cores, the thing that we just totally puzzled us was when we looked at it under the scanning electron microscope, so super fancy microscope, we found these crystals. And these crystals are what we refer to as halite. That's the mineral for salt, NaCl. And we all know that when you get salt in crystalline form, it would have had to have precipitated out of solution, and that happens through evaporation. You can't have water associated with it. So our results show that Lake St. Lucia, several times since about 4,000 years ago to about 2,000 years, has dried out completely. A massive change for what we expect, where we know that it dries out a little bit here and there, and this is probably one of the worst events, but it's not completely dry. And we see that this has dried out completely in the past. Really interesting understanding now how things are going to evolve towards the future. And this is what we think the lake is going to look like in times to come. A little bit of shallow water bodies by the way of like little isolated flays and pans, but mostly just kind of marshy wetland, not really a lake system. And then ultimately sea level will fall and we'll transform that back into rivers that'll cut across the continental shelf. And then sea level will rise. At that point, we'll be long gone. Who knows what will have inherited our place in terms of the evolutionary scheme, but they'll be documenting that geology as well. And this, I think, is my most favorite image I've managed to create out of this research project. So this is the seismic line through the lake. I'd like you guys to just focus your attention on this dark blob over here with these lines that are bending down. It's a classic seismic signal when you go across something that's really hard, really like sort of hard, blocky object that's sitting on the seabed. Initially, I thought I'd gone over a rock or something. I was looking on the computer screen. We were very excited with our heavily overloaded little rubber duck. And I turned around and I noticed that instead what we were visualizing was one of these little beasts, hippopotamus. So we just drove over a hippopotamus in about 2 meters of water. I don't know how we didn't hit it with the props. And this thing angrily appeared behind us. Now, many of you might think these things are quite cute and cuddly, and you have these sorts of cartoons which are incredibly misleading, but sorry to pop your bubble. That's the kind of thing you can expect. There's a hippo basically massacring its young. So they are not the most gregarious of animals. So you can imagine there we are in that tiny little thing, and we're beating a very hasty retreat. But ladies and gentlemen, that is the very first seismic signal or seismic identification of a hippopotamus. I can't wait to receive my Nature publication from that. So let's take this now a little bit further. We're looking at these water bodies, but now we're going to extend these water bodies out into the ocean. And we're going to look at submerged shorelines now, no longer raised above. So we're going to look at these beach rocks, and these are eolianites, but now these are occurring on the seabed. And on the left here, we've got a map of all of the various ones that I've managed to map in the last, say, 10 years or so along the Southeast African seaboard up to Mozambique. So we've done a lot of work on this over time. Why are these important? Because they're important. Primarily, they give us an indication of what sea level's been doing when it's been lower. They allow us to map those sea level conditions. So here's a multi-beam bathymetry map of one of these submerged shorelines made up of beach rock and eolianite. We can see this ridge that's formed along here, perfectly preserved on the seabed. And remember, we always say the present is the key to the past. And in this instance here, I keep having to move this. If you guys can hear in the background, that's my toddler stomping around, so don't get angry. If we look here, this is a modern day image of Seduana Bay. This is Jessa Point. This is where everybody launches to go scuba diving. This is made from LiDAR, similar to making these bathymetry maps, except we use lasers. And we see in here, again, the same shape, this coastline forming this kind of curve like this. We call that a logarithmic spiral bay or a headland-bound embayment. We see that preserved in the seabed. What we can then do is we can then infer that at the point in time when sea level was occupying down here, we had very similar wave conditions, sea level conditions, sediment type conditions as to what is occurring today. So we start to make great inferences like that. It's very important for us. So I'm not going to go into too much detail with these. I'm going to just show you that this is something that is occurring throughout Southeast Africa. So this is a map we're working now in northern Mozambique. We've got a lot of research work going on there, all of the tropical marine embayments. This is Mozambique Island. We've done a lot of mapping here now. And we can see quite clearly we've got old river channels crossing out. These are associated with very low sea levels out here during the last glacial maximum at about 130 meters below present. But interestingly, if you follow my cursor along here, there is a cliff line that's been cut in. And that cliff line is associated again with another shoreline, like the one I showed you previously, that sits at about 60 meters below present. We have another one that sits at about 100 meters below present as well. And these are regionally mappable from, if we look up here, all the way down here up to the tip end of Mozambique. We haven't gone into Tanzania yet. The idea of this is that we are looking at a stepped set of rises in sea level. To form these types of shorelines, we have to think about how things are forming nowadays. We have relatively stable sea level, even though we're all going, sea level's going crazy, it's rising. Yes, it's rising, but it's relatively stable compared to certain periods of the past. We needed those stable periods, like we have here with a relatively slow rising rate of sea level, to form these nice coastlines, to cut cliffs into things, and to form lovely log spiral bays and beach rocks and aeolianites. But to preserve these, we would need to then evoke rapid jumps in sea level. And these rapid jumps in sea level are related to things called meltwater pulses. And
you don't understand all.
so these meltwater pulses are associated essentially with these rapid collapses of the ice sheets, huge inundation of fresh water into the oceans, and very quick jumps in sea level. And we do care about this because we are worried about climate change, and we're worried about how sea levels are rising. And we can use these as analogs for what we might predict in the future. So here's an image. I love this image. This is an image of the City Hall in Durban or the City Hall in Belfast, depending on where you're from. It looks exactly the same. They're twin cities. This is after 4 degrees of warming, 2 degrees of warming. We can imagine that there was a significant amount of warming with these collapses in the ice sheets, something akin to those sorts of lines. And so maybe this is something that we're going to be expecting in the next several hundred years. A very sobering thought. Obviously, also related to some of the marine geology we do is the mapping of areas for marine protected areas. So obviously various animals associate with various geological type processes and geological substrates. So we map these areas out and we allow these to be then incorporated into marine and spatial planning design for marine protected areas. Here's one area here that sits between 2 very famous marine protected areas of the Amatoli and the Protea Banks. Marine and Mpondoland Marine Protected Area, and we hope that this map that we've made, and this is something one of my students has made, is going to help form a corridor of biodiversity between these in terms of protection. So let's get to the good stuff. Well, what's it like being on the water? Well, as you all know, you can get seasick. So I'm going to finish my talk. I know I've gone a little bit over time. I'm very sorry. It's hard to practice a talk with a toddler in the house. With the best to worst. So all the vessels I've been on, these 2 are the best. So the Norwegian vessel, the Dr. Fridtjof Nansen, with my colleagues from the Oceanographic Research Institute, followed up by the German research vessel RV Meteor. Those are great. And I think right then and there, we draw a very big line in the sand. Everything else that comes after, it's pretty tatty. This is the old University of Cape Town research vessel, the Thomas B. Davy, that we've used for many years, sold into commercial work. That's since gone to Nigeria. We get the South African vessel, the Algoa, which is okay. You know, I must say the Thomas B. Davy rates are better than that because I didn't have to share a shower or a toilet. That's pretty awesome. The next best seagoing vessel was a submersible. So for my PhD, when we were looking for the Coelacanth, tiny little thing, I could probably sleep on that better than I could on the Algoa. That was a lovely experience. We follow that up by the usual things. So our usual tetanus vehicles. I'd like in my acknowledgements to actually thank the tetanus vaccine for protecting me. It gets worse. So here we are towing a rubber duck that's broken down. Eventually getting to this sort of thing where when we have a strong wind, it's particularly unsteerable. And this is what I think is just the best thing about South African ingenuity. No matter how constrained our budgets are, we do, I think, world level, absolute cutting edge science with very, very minimal amounts of funding. Who knows what the future may hold? Maybe this is the research vessel NRF budget cut. Hopefully that's not the case. My favorite research vessel, however, is still going into the ocean and checking out the waves. It'll be my passion forever. And I hope this talk has given you guys a little bit of an idea surrounding that passion. I very much look forward to hearing some of your questions and hopefully seeing some of you in my classes stepping forward into the world of marine geology. Thank you very much for your attention. Are there any questions? Please don't hesitate to ask.
Thank you so much, Andy. And that was really an awesome talk. There are already lined up a few questions. And so the first one, let me just, okay, from Sipho. Sipho, you want to unmute yourself and ask the question yourself? Sipho?
Yes, I just wanted to ask concerning the seismological, that little that graph that you took. I mean, that data that you took. With the slide with the hippo. Why was that so interesting? And could you explain it a little bit further? Well, I don't know anything about geology, so.
Okay, Seabed, that's a good question. So if you can imagine, there's several things that make it kind of cool. Firstly, there's not many places around the world where you have hippos that are interacting in your field area. So, it's giving you that sense of danger. Girls like that, apparently. That's how I got married. More importantly, though, if you can imagine, you've driven over a hippo, and while you're doing it, you've got this machine that's going bang, bang, bang behind you. It sounds like a gunshot if it's on land. It's a bit muted underwater, but I don't think hippos are going to get all that excited about this just narrowly skimming their heads. And not only are you doing that, but you're actually creating this crazy acoustic picture of a hippo. And it's exciting to me because I don't think anyone has ever done it, certainly not intentionally. And I doubt that anyone has been stupid enough to have done this like we've done it, because there's no such thing, and sorry, Professor Modi, if you're hearing this, but there's not really a lot of health and safety that happens in some of these field trips. We do our very best, but it's Africa, it's real, and it's dangerous. And that's what I think makes this just such an alluring place to work, and why that thing as a symbol is something I always put in my talks when I talk to people from overseas, because it's just something so African and so cool. I don't know if that answers your question, but boy, you got me going here. Excited.
I don't know if you could annotate that little picture and tell us what's going on there. Like if you can bring it back to slide and just sort of.
So the way sound works is that when you're using this, it's low frequency sound. So it doesn't make a perfect three-dimensional rendering of something. What it does is you listen to the way the sound responds to changes in density with this seismic system. And a hippo is a massive change in density relative to water and very different density relative to sediment. So it's almost like a big blocky immovable object. And this is exactly where this is happening here. So I'm going to do this. I've been learning, guys. I've been doing a lot of online teaching for the last while. Let's try this. It's this feature here. And it's these things these are what we refer to as seismic diffractions. They occur when you find like a really hard object on the seabed. And that's what I saw. I saw these things and I thought, oh, maybe I've gone over a big block of wood or a rock or something. And that was when I looked behind and the little ears popped up and then the snouts and then the thing started chasing us. And I mean, like we were going as fast as we could and it was keeping up with us. I thought that was the end of days. It was myself and a colleague and a friend of mine on the boat. It was really an interesting experience. So I hope that annotation kind of helps. It's not exactly what you'd expect to see here with like, your hippo murdering its baby, but, it's what we would interpret as a geologist.
Simple answer. Does it answer your question?
Yes, thank you.
Okay. And Himanshu, do you want to ask your question? Because I think that is a very interesting question.
I was just very curious. I mean, the Latimeria really excites me, and having seen that, and we're looking at sort of billions or millions of years way back, what's the correlation between your geological habitat or substrate and the fact that the Latimeria is living there, the coelacanth?
That's a great question, and that was an aspect that it was intrinsically linked to my PhD. The coelacanth is indubitably related to geology. So it occurs in a particular depth zone, and that's controlled mostly by things like dissolved oxygen and sunlight, but it needs shelter. Coelacanth is a relatively slow-moving fish, so it's prone to predators, and it takes these shelters in things like submarine canyons or relatively irregular relief topography. So these submerged shorelines. So that's our theory that we are thinking, is that this thing migrates between these submarine canyons along these shorelines. But the submarine canyons themselves are super cool because they've got all these caves that have been notched into them from low sea levels. And those are the caves now where these coelacanths live. The coelacanths need that type of geology that influences the habitat. So habitat is intrinsically linked with geology. It needs that habitat dictated by geology to survive. And that's it. So when we find them, say in the Comores, they live on the slopes of volcanoes, but again there, it's extremely irregular, rugged relief type of material in which they live. Everywhere that we know them along our coastline here, the most recent discovery, I think, was in Mzumbi Canyon. We've got a beautiful map of Mzumbi Canyon as well now. And it's the perfect hiding place for coelacanth. So yes, they are 100% linked with that. And the funny thing is, when you look at the way the ocean basins have opened and our submarine canyons have developed, they've all developed from north to south, originating further to the north in the Comores, coming across into Africa, then making its way slowly further south as the conditions have become ripe for them. So they use these canyons as stepping stones. It's really cool. Like from a geological perspective, I think it's one of the most interesting aspects of looking at a habitat.
Okay, Mutulisi is raising his hand. He's got a question. If you just want to unmute yourself and ask your question.
Thank you. Thank you very much, Andy, for your interesting presentation. 2 questions. One is, I read that many countries fight over ocean or sea boundaries, especially when it comes to the resources that are there. Can your research contribute to a fair adjudication of the oceanic boundaries? That's one question. The second one, I read about oil drilling in the sea. Where is the oil exactly located? Is it at the seabed or somewhere else in the sea? Thank you.
Okay, Talisi, no problem. So yes and no for the first question. So yes, my research should be informing that. But the thing is that South Africa has such a limited budget. You know, we're trying to play with the big boys, but we don't get given the money to actually really play in those circles. To map out our continental claim, which is referred to as the exclusive economic zone, and that's several nautical miles out to sea. It's really deep water. You need proper ocean-going vessels with proper equipment on them. And we bought a brand new research vessel, the Gullis, to replace the one that always goes down to Antarctica. Do you think they put a multi-beam system on it? No. And so we don't have that capability ourselves to really map that out in detail. What we can do is we can use satellite data and that sort of thing to get good approximations. And that's how we do it. Likewise, the Council for Geoscience, which is the Geological Survey of South Africa, the erstwhile Geological Survey, they are responsible for managing and sort of delineating that claim. So they're the ones, their research and their statutory projects should really be fulfilling that mandate, but they too are somewhat hamstrung by financial constraints. So, you know, for us, it's difficult. But yes, if we had the equipment and the resources, sure, our research could very easily do that. But, you know, in many instances, it's quite cut and dry for us. It's places like Madagascar and Mauritius and Réunion, which is obviously part of France, where there's a lot of tussling because no one's really clear whose area overlaps what. So everybody's kind of at loggerheads over that. Those are the kind of areas where really, like, I think more intense research needs to be undertaken to examine that, what is it called again? You know, your economic claim. For the second question, yes, oil and gas drilling, but that oil and gas, firstly, if I could tell you where it's found, I definitely wouldn't be working at a university. I'd be sitting on my private yacht in my submersible. But usually, you know, we find that occurring in a particular kind of rock. And that rock would have to be sandwiched. That's usually a sedimentary rock, definitely a sedimentary rock. That would have to be relatively porous, so we'd allow fluids to flow through, and that would be where you'd store your hydrocarbons. And that needs to be sandwiched by layers of rock or sediments that are impermeable. So keeping it almost in a way like a groundwater aquifer, but that's where you store oil or you store natural gas. And that's the kind of thing that the guys are constantly looking for. Those things show up well in seismic lines and seismic sections. And there's obviously a multi-billion-dollar industry revolving around that. Usually the data that we get given is oftentimes proprietary, and you know, anything that remotely looks like it might have some oil associated gets cut off. So, you know, that's why we don't work very closely with the oil industry with their really big stuff, because it's just so secretive and also so expensive. I hope that answers your question on both counts.
Precisely. Thank you very much.
Okay, Gary, you want to ask your question?
Yes, can you hear me?
Yes, we can hear you.
Oh, good. Yes, Andrew, how are you, my boy? Good presentation. I was just wondering whether you and I looked at mission rocks a long time ago, but we never concluded anything. Did you ever reach a conclusion about whether it was due to a tsunami or some sort of event like that or not?
So, Jerry, that's a great question from the perspective of those big blocks are quite easy to move. You know, they're almost like airplane sails. They're big slabby things that can be lifted up quite capably. And when you apply all of those numerical equations to, you know, sort of a water mass that's going to transport those, it works out that you can transport those blocks quite simply by even, you know, our March 2007 storm. And so that was the conclusion that I drew, was it's very likely that a storm waves that have been essentially reworking and depositing those. And then when we did some real mapping, it looks like those things create a series of cells that find from very coarse to smaller boulders. And it looks like you actually have long, short transport cells within them. And I think, again, that was pretty conclusive for a storm as opposed to tsunami origin. But, you know, that being said, you can never rule it out. I mean, I was absolutely gobsmacked. You know, I came across this set of literature on this comet strike or meteor strike. And, you know, I've been working with a guy from Canada, and they discovered a tsunami in Tanzania related to, oh dear, here it comes. My son's coming in here. Yeah, related to what they think was this very much meteorite strike. And guys, that's why I went over time. It's impossible to concentrate. Yeah, and that's what got me thinking about these oyster deposits. So it's something I can't rule out, but I would say I'm 90% sure there was a storm wave origin.
Good, thanks very much.
Okay, so we've got quite a lot of. Any, are you still okay answering some questions, some more questions?
Fine. Tanya, I'm actually at this point in time, and again, please don't prosecute me, the higher powers, I'm drinking a cold beer.
Enjoy.
And I'm willing to answer.
Luckily, we're at level 3, so it is allowed. Archibald has another question, and then Stephen has his hands up. He can go after Archibald. Archibald, if you want to ask your question. Archibald is not here anymore. Okay, then I'll just move on to the next. Mohammed.
Hi, thank you. Hi, thanks for the opportunity. I've really enjoyed the series of presentations, I must say. I'm an engineer, so getting to play in other people's sandpits has been really cool. Regarding my question, you know, I love the presentation of, as you showed, the evolution of technology, and I was wondering, are we now considering options of using other waves in the spectrum to kind of ascertain what kind of rock we have under the seabed?
Mohammed, that's a great question. And so, you know, I've used kind of what we have available to us, which is pretty much the cutting edge technology from this aspect. But there are many other different geophysical techniques that we can use. We can use magnetics, which is again relies on rock properties and sediment properties to visualize things. And that's really useful when you're looking at things like changes in bedrock. And particularly where we have like faults and, you know, really like distinct boundaries between different rock types. And in particular, if you're looking for things like heavy minerals, or God forbid, if you're looking for offshore gold, and trust me, there is offshore gold. Really cool kind of thing to look, because you can find magnetic anomalies relative to that. From a perspective of just looking now with using sonars, the advancements are amazing. So that guy, Peter Ramsey, he's my great mentor, and the guy that just really gave me the push in life that I needed, just a great human. He is now developing these sorts of things. I'm an amazing man. And the stuff that they're doing with physics is just incredible. It's so far beyond me. And like, you know, amazing stuff where if you thought that it was cool to resolve something like a teacup, now you could probably go down there and resolve a couple of little like 2-cent coins that are lying in the bottom of their teacup, just because they've worked out ways to suppress the way in which you emit noise from your pulse emission, as well as the ways in which you can listen for that noise and filter out things. It's just incredible. So, you know, there really is a huge amount of progress still being made. The one cool thing that's being made now is what the guys call mapping the thin white line. So we can map up to a point, then things get so shallow and so dangerous with waves that are breaking and that sort of thing, that you can't map anymore. You can't drive a boat in there. You can drive a jet ski maybe, but like that's the data is usually rubbish. And then you can map from the coast on using LiDAR, so using light laser. They've got a bathymetric laser system that is incredible. You shoot down these lasers, and it's a blue and a green laser, I think it is, and you work out the phase difference between these, and it allows you to get an extremely intricate picture of the sea floor exactly in that area where you can't map, that white line that joins the coast and the ocean. And that is something where I think people will be moving forward with, but the only problem is it only works in areas that are extremely clean with regards to the water. So the water has to be very clear. Can't have lots of sand or sediment moving around in there, can't have lots of breaking waves. So that is another big advancement, and it's something that's really expensive. I don't think South Africa has a system for that, but I'd be excited to try and give that thing a bash. But there's all sorts of cool stuff. Using multispectral imagery from satellites to try and extract bathymetry. It's not as accurate as multi-beam, but it's obviously much cheaper if you have a multispectral satellite that's orbiting over your country like the United States. Yes, huge advances. You know, no doubt by the time where I retire, I'll be looking back going, wow, look at these young whippersnappers coming out and doing cool stuff. It'll long overtake me.
No, thank you for that answer. I think that's great. I think if you just add that into the advancements that are going to come with perhaps AI in terms of interpreting the data, the future does look bright. So thank you.
Okay, Stephen, you're up next. Your hand is up for quite a long time.
No problem, thanks. And thanks, Andy, for the presentation. Actually, to tell the truth, my question was very similar to the last. It was trying to get a feeling of where the technology is going, and I specifically was interested in satellite-derived bathymetry, Andy, and where we might land up there, what the current constraints are in terms of water clarity and depth. But how quickly you think we might get to working at meaningful resolutions on a system scale, for example, like St. Lucia?
Yeah, Steve, that's a great question from the perspective of like a fairly large system like the St. Lucia water body. But I think the footprints, and I mean, okay, granted, if you look at the bathymetry in St. Lucia, it's very coarse because it's just so shallow and it's just a mission. If you're trying to get like a really good bathymetry in there, you're using a single beam echo sounder, can't use a multi-beam for the whole system. Basically, you're going to be there your whole life trying to go backwards and forwards in parallel lines. Something like a satellite-based system where you can do that inversion on that satellite data is obviously quite attractive. I just think probably what's limiting that is the fact that that water is just so turbid. Something where you have cleaner water, like some of the shallower, cozy lakes without so much of the organic debris that gets you, might be a better option. But yeah, St. Lucia, I think, is going to be one of those systems that's just going to require serious effort. And like the data collected for the GEF project is phenomenal. I mean, it really is. And you do get some bathymetric return off the LiDAR, around the banks and those sorts of things. But overall, the bathymetry is quite coarse, and it's never going to adequately describe that bathymetry to, the point of something like a multi-beam survey. And I do think you would have better resolution with something like satellite inversion, but I don't know. The only person I know that actually has experience in that is my friend Carlos. He's listening in, and he's probably the guy to chat. He's written a couple papers on that, but yeah, from my side, Eva, I don't know really if it's possible. I don't think so.
Thanks, Andy. And Nazia, if you want to unmute yourself and ask a question.
Hi, Andrew. I was just wondering, did you ever get to work with seismologists around the world or here in South Africa?
Okay, so a seismologist is maybe slightly different from what I do. So I use the generation of seismic waves, which is something that they also do, in terms of understanding earth tremors and earthquakes and that kind of thing. But don't really overlap a lot with seismologists, unfortunately, though. What a cool and interesting career to be in. I mean, imagine that, monitoring earthquakes. So I haven't really had a chance to work with those guys, though I know a couple from WITS. That's the main center where people work for that. They've got a fantastic geophysics department there. But yeah, in my own field, yes, lots of people around the world in particular. This has been a real magic carpet ride for working in this field, looking at, so basic geophysics and acoustic geophysics, so seismic reflection and that kind of thing, which is what this big squiggly line is in front of you on your screen. Yeah, fortunately, no, not a lot to do with seismology. I'd love to, though, because we do use seismological data, in particular when we're looking at, say, tsunami threats and those kind of things, but maybe in time.
Does it answer your question, Nazia?
Yes, thank you.
Okay, Konto, you are up next, and you have a very interesting question for Andrew.
Yes, hi Andrew. I was just wondering if you guys have ever found any evidence that there were islands that were buried, maybe due to the changes of the sea levels.
Did you get this, Andy? So he was asking if there've been buried islands due to the changes of sea level.
Okay, so I'm going to go out on a limb here and say yes. So interestingly, you can have all different kinds of islands. You can have islands that are made of bedrock or islands made of sand. And those islands that are made of sand, we refer to on like our sort of coastline where you've got lots of waves. We call those barrier islands. And I found many barrier islands that have been preserved on the seabed. So, these really cool things. So do yourself a favor. After this, go and Google something called Galveston, Texas. That's where offshore of Texas, where all the oil refineries sit. And that's what we call a barrier island. It's an island of sand that just sits away from the mainland. We find those things preserved in the seafloor all over the show. If we take a more traditional view of what an island is, which I'm probably guessing that's what you're thinking, like something like the Maldives, really interestingly, yes, you also find those that are actually left behind on the seabed from these rapid rates of sea level rise. So yeah, we do find those. Find all sorts of cool stuff like that down there, like buried islands, buried barrier islands. What was the coolest thing I've ever seen? An entire buried system that looks just like the Cozy Bay Lakes. So again, have a look in Google Earth. Found one of those in the seafloor directly offshore of Durban. So, the miracles that can be revealed when you actually have a bit of equipment that can visualize things in 3D is just fantastic. So yeah, I hope that answers your question.
Yes. You answered my question. Thank you.
Meli, you want to ask your question? I know that you had your hands up and you also posted a question.
Yes, thank you for the opportunity. Yes, I was asking about if you found any evidence or suspicions about alien habitats on the seabed, because I always see the regular strange lights heading to the coasts from the sky.
So let me get that right. So if I find alien habitats, is that correct?
Yes, or suspicions. If you suspect maybe yes, if you suspect anything out of this world that we don't know of that lives in the ocean from the sky.
So my biggest suspicion of an alien is probably my 17-month-old son. I've never seen anything behave like that, but he lives on land. But under the sea, probably no. I'd imagine that trying to find an alien habitat down there, they'd be pretty sneaky in terms of their camouflage. In particular, if you could live under the ocean and fly in from space, I don't think you're going to want human beings finding you. So no, I can't say that I have. But if I did find it, again, probably wouldn't be working at a university. I'd be living in luxury down in that alien habitat, drinking an alien martini or something. So no, I can't confirm, nor can I deny that question.
Okay, and Nazia, you're going to have the last question. Okay. Nazia, do you want to ask your question yourself or do you want me to read it out?
Hi, sorry. Are there a lot of job opportunities in marine geology?
Now, Nazia, that's the $1 million question, isn't it? So this is a country that has some sort of strange and somewhat backward ideas in terms of what constitutes marine science. So marine science is actually quite adequately funded if you're a biologist or you're an oceanographer. But the big thing that marries all of that together is geology. And that's the thing that's, I think, suddenly becoming more and more apparent to people, is that we just don't have South Africans to do this job. The fact that there's one university in the whole country, and actually one university out of the whole of the continent, that has all of the equipment we do, produces students as we do, and actually studies marine geology, is kind of testament to the fact that this has been very much under prioritized. But what's happening now is the government has woken up to this. We know that we need to utilize something that we call the blue economy. So that's the economy of our ocean. And the economy of our ocean is such that we need to know what the seafloor looks like. We've got to know what's down there. What are the mineral resources? What are the biological resources? What must we conserve? What can we mine? Where does it all go? You know, so fundamentally, that is a geologist's job. There is no chance a biologist or an oceanographer can do that. It's like me dabbling in sort of species evolution and genetics. It's impossible. So yes, there is certainly scope as we move along in life, and as the government is awakening to the idea of this blue economy. You know, jobs are definitely opening up. So for me now, we forged very, very strong relationships with the diamond industry. So just tomorrow, I have several students that are heading off to Cape Town. We're organizing a 6-week cruise to go look for diamonds along the southern Namibian coastline. They'll come back. December's another one. We're working with De Beers, we're working with their competitors. There's lots of scope for people who can be relatively creative and inventive, like going onto the sea, enjoy this sort of thing, to make a mark. It's really, in my opinion, slowly starting to emerge from something that was very government controlled, so controlled by the Geological Survey and pretty much just them, to now a very broad field that's opened up. And interestingly, and you might like this if this is something that you're interested in for geology, the petroleum agencies, so the guys that control all of our petroleum wealth in the country, they fund us now. Every year we get about R500,000, and it's to teach you guys as students, and I presume you're a student, you sound quite young, but don't be offended if you're not, to teach students how to do what I'm doing here, to allow us to all go to sea for 2 weeks and to put our equipment in and to figure out how to switch things on, switch things off. Because every time we try and drill a gas well, every time we go out and we try and situate a monitoring pipeline, we have to hire people from somewhere else to come and do this. Whereas we can grow our own talent. And that's the thing that suddenly the government has realized, you know, we can prioritize that. So if this is the last question, I think it's a fantastic question to end on, because for me, I see the sky being the limit. The limit for a number of different career opportunities, from environmental stuff through to geological, to mining, to protection, to archaeology, just fantastic opportunities on the horizon. So yes, I think a very positive future ahead.
Thanks, Andrew. If you can just stop sharing your screen so I can share my screen. And I just want to close. Okay, Andy, if you can just stop sharing your screen, please. Thanks. And I'm just going to share my screen, because I want to invite you. Usually, you know, at the end of each talk, we have a fantastic buffet. Unfortunately, due to COVID, I can only invite you to a virtual buffet. So I brought some special yeva for you, Andy. I hope you appreciate this.
It's still my most favorite beer.
All right, we are coming to the end of our lecture series, and I would like to take this opportunity to thank a few people. First of all, a huge thank you to our guest speakers, Professor Mike Brooks, Ms. Tenkizu Mosa, and of course to you, Andy, so Professor Andrew Greene, for some really, really amazing and inspiring talks. And for those who've been here for the last 2 days, they know what I'm talking about. We put the talks online, so you can check out on our website. Also to Dr. Sally Frost, who coordinated this event. While I was, you know, in the field and playing with rocks, my sincere thank you. She also had my back covered during the live sessions. So she was the person who was muting and unmuting people and, you know, be there. To Ashok Raj, who designed the invitations and wonderful backgrounds, a big thank you. To the Department of Science and Innovation and SASTA for providing such a great opportunity to highlight the science and engineering that we do here at the university. And to the countless people in the back who helped spreading the message of, the talks, and by the number of people that we had during the last few days, it was, I think, a huge success. Thank you so much. With that, I conclude our public lecture series. And here's young Andy. Oh my word, he's so cute. Thank you so much, everybody, and enjoy the buffet, enjoy whatever you drink, if it's alcoholic or non-alcoholic, and enjoy the rest of your evening. And thank you very much for joining us tonight.
Thank you, Tanya. Thank you to you.